Okay, I'll be quick. So I'm going to present the work of Marcus Williamson, who can't attend the meeting, unfortunately. And this is work in collaboration with Diamond Light Source, supported by Nuclear Laboratory and EDF. Clicker for next slide. Actually, it's probably that one. Okay. It's about graphite, nuclear graphite, used in the UK for the Magnox and the AGR reactors, which are CO2 cooled, also being used in future for high temperature reactors. Important material. Why graphite? It's a structural material with good neutron moderation and low neutron absorption, and it has excellent thermal shock resistance. So its structural properties are really interesting, and its effects with radiation are really interesting. Now, graphite is an interesting material. Its crystal structure we know very well. It's highly anisotropic, which means its elastic and thermal properties are also highly anisotropic. For example, if at the Young's modulus, it's about 1,000 gigapascals in the plane, about 30 gigapascals out of the plane. The way you produce your graphite affects the properties of the graphite. So as we change the graphitization temperature, graphitization time, different raw materials, we will get a different graphite structure. And then we look in details at graphite. We have this sort of crazy paving arrangement of aligned crystallites, very strong texture, and massive accommodation porosity at the nanoscale because of the very large internal strains that develop as we cool down from graphitization. In fact, it's these which give graphite its fantastic properties because it gives us a very low elastic modulus. Okay. The interesting thing is, as we increase temperature or irradiate, the swelling of the graphite crystals will close up the porosity and change the microstructure and change the mechanical properties of the graphites. So again, graphite's interesting. Furthermore, it's full of porosity. This is the AGR graphite, where if you use it in a carbon dioxide environment, we get massive changes in porosity. In the helium-cooled reactors, there are conditions where porosity can also change. So again, the structure of the graphite changes over time. And then when you irradiate it, it does even more interesting things. Graphite in the unirradiated condition has non-linear elastic properties and non-recoverable strain. You irradiate it, the stiffness increases and that non-linearity disappears. Also, if we look at the effects of temperature, ignore the very high temperature stuff, but its strength increases as you go up in temperature. This is interesting for material scientists, okay? It also means that you can't predict how your graphite is going to behave. You can do tests to get data on how irradiated graphites will give you, the properties. You can extract bits of material from an operating reactor. We need to measure, and we need to make measurements in small specimens because there's not a lot of irradiated graphite out. A, because it has to come from test reactors, or B, you have to cut it out of an operating reactor, and the operators don't like it if you take a lot of graphite out. So what's our interest is how do we measure the high temperature mechanical properties of graphite to sort of design and qualify new graphites and to monitor existing graphites. So we squash it. We're focusing today just on the high temperature stuff, but our long-term goal is to look at cyclic loading and irradiation. We need to do small specimen tests. So we're working really following the Brazilian disk or disk compression geometry, which is of interest to the Gen 4 International Forum, where it's a standard way of measuring tensile strength, but it uses a very simple elastic model, assumes elastic contact, doesn't tell you anything about the stress-strain relationship, and basically says, here's the size, there's the load, there's the strength. Is it right? We don't know, so we're trying to find out. We're doing the tests at the Diamond Light Source, where essentially we have an ETMT, electrothermal mechanical testing device, passes a large current through the sample, heat it up. We can do diffraction in transmission. We can also do radiography and study the sample in situ. So here's a sample between some limonic grips, which will then squash. This is what it looks like at around about 800 degrees C. It's thermocoupled. This is one of the candidate graphites. This is a 5mm diameter disc, about 3 mil thick. And we're doing diffraction and radiography in situ. Diffraction in transmission, we're just focusing on the 002 ring or the plane Debye ring. We get information on the position and the intensity as we go around the ring. And we can map the surface, map the sample with about 100 micron step size and cover about 2 or 3 square millimeters quite quickly. We also do radiography. We'd love to do tomography, but this current device doesn't let us spin the sample around, so we do radiography. Graphite has quite a good structure for image correlation, but we do help it by putting a bit of tungsten powder on to give it a bit of speckle. And that means we can get digital image correlation. So this is the kind of data we're collecting as we go through the experiments. What do we find out? This is an analysis of the DIC data. So these are the strain fields we calculate from the gradients to the displacements. Just example data at different compressive loads. This is the tensile data across the top row, the compression, which is in the vertical direction, along here, and then we get the shear strains out as well. We are looking at the full field data, but I'm going to focus most of what I say today about what's happening in the middle of the sample, where, as you can see, the stress state is reasonably uniform. And we develop tension, we develop compression, and so on. Okay, so that's the image. That's the imaging. So that measures the total strain the sample is receiving. And then if we go to the next slide, the diffraction, we can map, again, the strains in the horizontal direction, the strains in the vertical direction, and the shear strains going around the ring and identifying the principal strains, which actually turns out to be very well aligned with the loading we get. And the sharp eyes will notice that, yes, we can see the compression in the vertical direction. There's not much happening in tension, which is not surprising because we're compressing the sample, it's splitting, getting fracture, and when fracture, of course, occurs, you can't sustain much tensile loads. So this is telling us and allowing us to see the effect of cracking in the sample. It gets more interesting when you put the two sets of data together. So here we're plotting the crystal strains measured by diffraction against the total strains measured by imaging. In the compressive region, it's nice and elastic. We actually see an increase in the stiffness at a high temperature, quite significant at 80 degrees C. In the tensile region, as we put quite large tensile strains on the material, we can see that actually we get a saturation of the crystal strains. So essentially it's fracturing at a constant stress. What's quite interesting is we tend to get quite higher stresses at higher temperature. The graphite is stronger at high temperature. That's what we expected, it's what we're seeing. There's a bit more that we can get also from the diffraction. If we go around the ring, we get the variation in intensity as we go around the azimuth. That's telling us something about the anisotropy of the graphite. We can quantify it in several ways. The standard way is the Bacon anisotropy factor, where you basically plug the data into that equation, and this maps the local texture. We can also look at the intensity ratios, what's the intensity in the vertical direction, horizontal direction, to see how the texture is changing. And we can also look at where the maximum intensity is rotating round to. Okay, so what do we get when we do that? This is just showing how the anisotropy expresses the ratio of I90 to I180 is changing. And we see the anisotropy is changing. Essentially, a larger proportion of the crystals are aligned to give Bragg diffraction with intensity in the vertical direction. They're orienting themselves perpendicular to the loading direction. So the crystal orientations are changing as we load the graphite. We get the same thing when we look at the Bacon anisotropy factor. Again, if you just look at the middle of the sample, you can see the trend as we go across. The anisotropy changes as the compressive strain increases. What's interesting is it doesn't depend on temperature. You know, the graphite texture is changing in accordance with the strain. We're getting the strains at different stresses with different temperature. There's no change in the mechanism. And then what's happening? Well, we think it's something simple as just Taylor crystal rotation. Graphite has very, very easy basal shear. We have a very textured microstructure, but again, we have constraint of the crystallites with each other, so it'll tend to rotate. So we get this gradual rotation because of the strain we're applying. What's more interesting is when we look at local changes, because actually there are some quite consistent, significant changes in crystal orientation as we apply strain. When we look at the fractography, we see evidence of kinking of the graphite. So we're seeing evidence as we apply more and more strain to the sample that certain regions are changing their orientation very significantly by this kinking behavior, which we've seen before. This is nanoindentation applied to HOPG. It's basically aligned graphite crystallites, so we indent on the basal plane. And as we go up in temperature, we get a massive change in the way the graphite responds to accommodate the deformation indentation. For example, here's data at 60 degrees, here's room temperature. And what's happening is there's an increased ease of kinking of the graphite crystals. So it's a strain accommodation mechanism. So what do you think is going on? We've shown we can do full field measurements in small specimens in situ at high temperature, and we're working on the data using the virtual fields method to basically pull out the stress-strain relationships from it. We've shown that the elastic modulus increases at high temperature. That was expected. It's because the porosity is closing up with the swelling of the crystals. We've shown that we get higher tensile strains at high temperature. Again, that's consistent with the observation of higher strength. And we've shown these crystal rotations, the small and general ones because there's basal glide Taylor effect, and then these local effects of kinking. Why is this interesting for us? Well, this shows how graphite fractures. This is a high-speed tomography test we did recently, a few years ago at the Soleil synchrotron. Each tomograph is 2 seconds, and you can see graphite fractures by propagation of cracks and stress concentrations, defects in the material. What we believe, maybe wrong, what we believe is that because we've got these mechanisms for deformation of the crystal at high temperature, it provides essentially a strain accommodation mechanism, which means the graphite becomes more tolerant to stress concentrations. That means it has higher strength. Are we right? We don't know. But it becomes interesting because this all depends on basal slip. And we know that neutron irradiation strongly affects basal slip. So what's going to happen when you irradiate the graphite? That's our next step. For a reactor operator, this change in texture with strain is actually quite important because this texture affects thermal expansion, affects thermal conductivity, it affects the radiation dimensional change. These are loaded components, stress components. It will affect the way stress evolves inside the microstructure. So these rotations are quite interesting. And our long-term goal is to look at cyclic deformation. Why are we doing all this? Well, actually, it's very nice doing stuff on the synchrotron, but you can't take it to the reactor. You can't, they don't like you taking irradiated samples there. Our real goal is to basically use this to validate optical techniques, which can then be used with high temperature testing and inverse modeling to qualify, quantify the behavior of graphites. Thank you for your attention.